Okay, we introduced in class this problem of taking a long segment of length L plus 1, scattering points along it randomly, and then placing unit intervals on the segment and observing the properties of coverage for those unit intervals with respect to those points. So picture would be something like this. You've got an interval of length L plus 1. You put down random points, which are the blue, and then you lay down random intervals, and you see which points they cover. In this case, it covers this one, perhaps this one. Lay down another interval over here. This one perhaps just covers one point. Now, all these intervals should be the same length. Sorry, they don't look the same, but they should be the same length. This interval covers these two. So we're looking at the properties of these intervals vis-a-vis the random points that are there. We can ask various questions about that. Now, we started asking last time. The first question we asked is, how many different possible sets of this form are there? And you got an answer to that, or you created a program that can answer that. So we had several other questions that I proposed, and I'm going to give you in the following videos some idea about how to attack these problems. All right, so the first problem, we define various parameters. Just remind you what they are. M is the number of simulations. That's the number of times that you throw down a unit interval and see the result. D is the density of points. That's the average number of points per unit interval. The length of the segment is L, big L. So typically big L would be much, much bigger than 1. And we created a vector to contain our results. And we generated a vector of random points, which is fixed during the simulation, and that's called ptvec. And actually, once you find the segments and their position relative to the points, you don't use ptvec any longer. All right, so what you do first is you loop over your trials, that is, loop over intervals, and you generate random left-hand interval and so on. I'm not going to go back over this because I think that you have created this code. The upshot is that you have a vector iVec that contains all the information resulting from that simulation. Now, from iVec, you want to identify the unique entries, and those are the different sets of points that can occur when you lay down an interval of length 1 on this large interval of length L plus 1. So I want to call this number of unique entries U. So that's the U is a number of unique sets. And the question is, of these unique sets, of which there are many, what's the histogram of probabilities? How often do they occur? Is there some regular distribution for their occurrence? So that's what this next set of bullets will help you do. So first you create a vector containing the unique values in iVec. iVec is going to have duplicate values because you may get the same interval more than once. For example, this interval here contains just one point. But if I had moved the interval over slightly like this, I would get the same point. I'd get the same result. Same here. If I gotten an interval over here, I would get the same result. So you're going to have some probability, non-zero probability, of getting the same result multiple times. That's what we're trying to look at. So first we'll create the vector containing the unique values in iVec. So that's this encodes the information of the distinct sets here. In fact, this contains basically the leftmost point and the rightmost point in this set. So here you're going to have a set of values in this vector uvec, which is of length u. All right, now we're going to create a vector set count of length u such that set count of j is the number of times that the jth value in iVec appears in iVec. Sorry, that shouldn't be jth value in iVec. That should be jth value in uvec. Sorry, let me do that. Change that. The jth value in, where are we? Jth value in UVec appears in IVec. So you can do this by looping through the entries of UVec. Okay, so you're going to have a loop where you look at the entries of UVec one by one and see how many times it appears in the vector IVec. And then you'll take that result and put it in set count of j. So again, the number of times that the value of UVec of j appears in IVec, you set that value to equal set count of j. Right? So set count of j is going to be a series of numbers. Where each number in set count of j indicates the number of times that a particular unique set of points occurs during our simulation. So I'm not sure what size these numbers may be. That's going to depend on the number of simulations you do. If you had, say, 100 distinct sets and you did 1,000,000 simulations, you would expect about 1,000 counts per set. So, but if you do more or fewer sets, fewer simulations, you're going to get a bigger or larger result. But at any rate, you're going to get a distribution of numbers. This set count is going to have integers that you can do a histogram for. So you go ahead and create that histogram and see what it looks like, and then we can discuss what this is showing. All right, so that's the first task. I'll make a new video for the second task.